welcome to the afternoon session. We now go through other parts of the course. As I said, we don't have the time to go through everything. In the morning we had an introduction to climate and time series. We had the notation, T of I, X of I. We learned about the climate equation. Climate comprises trend, extremes and noise. The noise scales with a function called the variability, climate variability. And we learned about the distinction between what statisticians call the process level, the cap X, the climate, the system, and the sample level, the small t and the small x, the actual numbers of our sample. And the task of statistical analysis in general and time series analysis in particular is to learn about the data generating process, about the climate. And we had a first meeting with statistical language, noise and distribution, and we saw about the distribution of climate data, that often we have non-Gaussian shapes. And then we had the memory, cold today, cold tomorrow, and also on longer time scales. And now in this second chapter, we briefly touch these memory, the persistence. We make mathematical models, persistence models, for describing, for putting into a quantitative form the memory. And so I will proceed through selected parts of this chapter 2. And then we have also only the very beginning of the next chapter 3. And then we have to see, I hope that there is time to do some mini exercise. Let us proceed now without much ado. And I put the chat screen on the other screen I have here, though the chat is here. So it's your comments can now be seen. Okay, so let me proceed. And make this small. Okay, now we make a model for the memory. A model is an equation or a set of equations. And here are two equations. And this is the first equation, and this is the second one. The first equation reads, I read with you, x noise of 1 equals epsilon. So this symbol here is a Greek symbol denoted as epsilon, and it has an index n 0, 1. So of 1. So this is a first data point. I is equal to 1. Okay? And the other cases are treated here. So before we go to the second equation, let me explain the innovation term, this term here. This is a Gaussian distribution, n stands for normal or Gaussian distribution, with mean mu. So this again is a Greek symbol, mu, and with variance sigma squared, okay? And in this case, this equation here, the variance has a mean of 1, and this is the 1, and the mean has a value of 0, okay? And then this distribution looks exactly as that one here. This is a PDF, a Gaussian PDF with mean 0 and standard deviation and variance equal to 1 to unity. It is called a standard normal density function. Okay, and this arrow here, for example, this is the size of these of sigma, of the standard deviation. So this function is defined as here. Perhaps you have seen that in a textbook. And in the case mu is equal to 0, you can forget this. Sigma is equal to 1, you can forget that. Then you end up with this equation. Okay, what does this equation tell us? Let us have a look on the equation. F of x depends just on one variable, on x. And if x is very, very large, maybe 10 or 100, then the exponential of minus x squared, that means minus 10,000 or so, it's very, very, very small. It is almost 0. It's not exactly 0. It is 0.0000000 and so on. 1. Yeah? And the same also for larger negative values of x. Minus 10. Minus 10 times minus 10 is plus 100. So then again we are at exponential of minus 100 over 2. So you immediately see, if you look on this equation, it is a symmetric equation. It is symmetric by 0, okay? Because it doesn't play a role whether x is positive or negative. It's symmetric. And the maximum is obtained for x equal to 0. Then you have the exponential of minus 0 over half, which is the exponential of 0, okay, and which is 1, okay? Therefore, this value here is exactly 2 pi and then 1 over square root. Okay, so this is a function, the Gaussian PDF. Now, and you see the first point, let me now take another color. The first point here, no, I'm not happy. The first point now, it is a complete random draw. Now we come to the second point. I is equal to 2. What about this point? Well, look on the equation. X noise of 2 is given by A times X noise of 2 minus 1 is X noise of 1. Plus, and then this innovation term. And this factor here, this is a memory factor. If A is very large, that means it goes against 1, then you have almost the identical value as before. Okay, and this is the innovation term with mean 0 and variance 1 minus a squared. Now let us consider really the case a goes against 1. Then the variance of this expression 1 minus 1 squared is 0. It has 0 variance. It is identical to 0. Okay? And then this value goes against 1. That means the next point is identical to the first point, and the third is identical to the second, and the fourth is identical to the third, and so on. All the points are identical. Perfect memory. So 1, you can call this perfect memory. Okay? On the other hand, if a is 0, then you would forget everything. You have no memory at all, and you only have innovations. Okay? That means this parameter a, the AR1 parameter, it measures the degree how well you remember. Okay, the naming. It is called first order autoregressive model. Okay? Autoregressive means I remember my own past, and first order means I remember just the immediate own past, just the previous point. Okay? This is and you call this first order autoregressive model, or first order autoregressive process, or short AR1 process. So this is a typical way how to write it. Let me proceed. And now we will study some properties of this process. Okay, this is a AR1 process. I should say also for even spacing. So time is not, you don't see the time variable contained here. So let us now calculate the mean for the different noise values. Okay, we study properties of the AR1 process, and let us first study the property mean. We wonder, is it a constant or is it not constant, and what are the values? Okay, now what is the mean? The expectation of X noise. Maybe I make it a bit smaller. This. No. What is the mean of X noise of 1? Anyone an idea? You have it directly here in the equation. If you look at it's a defining equation. It's this equation here. So it's a random innovation, and let me go back. This is a mean, this epsilon, this is a mean value. This is what I want to have. So it is, anyone wishes to write it in the chat or saying it? Yeah, okay, then I will answer it. It is 0. This is this one, okay? Okay, and then we calculate the expectation for the seconds. I have to be careful now with writing. Of 2. This is, so they say the expectation of this all is 2 and 2, okay? And 2 minus 1 is 1, therefore it is. And then the expectation of the sum is the sum of the expectation. This you have to kind of believe me, or you find it in textbooks. Therefore, we deal with A, expectation of A times X noise of 2 minus 1 is 1 plus the expectation of this epsilon n okay, and then we next line we can put this in front because it is just a constant and the mean scales A times expectation. I don't know what that is. No idea. Excuse me, I'm still, okay, now it's away. Expectation of X noise of 1 plus, and then this one we keep. Now I insert the values and I use a color. Let's take green. Now we know the expectation of that we've learned here. This is 0. And this one, the expectation of that one we also know. This is 0 again. So it's A times 0 plus 0, which is 0. And so on. All the values have a mean of 0. And it's a similar mathematics to prove that the variance of the points is 1 for all points. So this is the variance of the first point. I just draw you the formula. And then the variance of X noise of 2 is given by A squared times the variance X noise of 1 plus, and then we have this one here, 1 minus a squared. I use another color, maybe black. And therefore, and the variance of this one we know, this is 1. Therefore the variance, excuse me, I hope you come with me. The variance is hence given by a squared times 1 plus 1 minus a squared. So this cancels out. Therefore it is 1. And so on. So this, therefore, the process enjoys properties constant mean, 0, constant variance, and square root of variance is called standard deviation, constant standard deviation, unity 1. It is called a strictly stationary process. The properties do not change over time. So this is a good thing because this is the assumption we put into the climate equation. Let me go back to the climate equation where we have it. Maybe here. It is here. Here, this one we have assumed when we formulated the model that the expectation is 0 and the variance is 1. Because we put all the variability, the variance into this climate variability S. And we see that we indeed can formulate a mathematical model that fulfills these conditions. Okay, maybe I also show you this one here. This is now a lengthy formula, but please don't get nervous. This is a function rho of h. This is called autocorrelation function. This is a property of a stochastic process, and this is a definition. I just put in the definition. This is a product here, so I take another color, green. This is a product, okay, and this is a time-lagged I plus h, yeah, h is a time lag, it is value 0, 1, 2, and so on, and this is a current one, I. Okay, and then we divide by these variances. But we have seen that the expectation is 0. You can't forget this. Expectation is 0. You can't forget this as well. Variance is unity. And if you divide by unity, you just can't forget this as well. And what results hence is this one, the autocovariance. Okay, and one can show, we don't do that here, that this function rho of h for an AR1 process for even spacing has this dependence, a to the power of the absolute value of the time lag. Okay, that means, how does that function look like? What is the rho at lag 0? This is a rho of 0 is given by a to the power of the absolute value of 0. The absolute value of 0 is 0, and something to the power of 0 is 1. Okay? And then rho at lag 1, h is 1, is a to the power of 1 is a. And therefore rho of 2 is a squared, and so on. So we can easily calculate this. Let us have a look. And this is again the defining equation, and with the help of a random number generator, usually these numbers are uniformly distributed, okay, on the interval between 0 and 1, and then you do a transformation, and then you can make a Gaussian distribution, okay, by a transformation. Okay, and then using a Gaussian random number generator, I drew these random numbers, which I then plotted in the book, in the figure. And this is the theoretical, the autocorrelation curve. One, perfect memory, it's clear. After 0 time steps away, I know, or at least I should know, perfectly about myself. Okay, and then you see that rather fast decay. A squared, I think A is a value of 0.5, 0.6 something, and then after a few time steps it approaches 0. It is always positive, we see this on the curve, but it can be very, very, very small. A fast decay, a short memory process. Okay, this is a AR1 process. Are there questions? Let me proceed. Now we come for the first time today in this lecture on one of the fundamental aspects we climatologists, applied statisticians, are doing. We make what is called an estimation. Yeah, we have data, a time series, or maybe we have the residuals, okay, and let us call the residuals here by x noise of I. We have a sample from 1 to n. This is our data set, and now let us make an inference on A, on the AR1 parameter A. And this is a recipe. A hat. So this simple here, this is called a hat. And this is a recipe. Take the product of neighbors and then sum over all neighbors, and finally divide by the sum of the squares over the same number of points from 2 to n. Okay, you see that the sum has to run here starting at 2, not at 1, because then this I would be 2, and I minus 1 would be then 1, which is available, okay, which is existing. But if I would be 1, then the second term would be I, x noise of 1 minus 1, x noise of 0, which does not exist. Hence, the sum has to start at 2. This is always a check. If you check a paper or review a paper or write your thesis, this immediately you see, I forgot, for example, if you wrote a one, this can't be true, or this can't be true, I have to replace it. Okay, this was a typo, and this is a way of correcting yourself. Okay, next one. Yeah, now let us come to the question, is that a good description, the AR1 process? Is that a good memory model? We will learn later that there exist other models and how to decide. And there exist statistical tests for doing this, but let me stress that graphical tools are very important. In general, it is always a good idea if someone sends you new data, or if you measure own data in the lab, do graphics, make a good plots of time intervals or the full interval, and then then do the estimation and the judge guided by these graphics, because the human eye is very powerful. Okay, and in this case we calculate what is being called the white noise residuals. Okay, this we did we estimated A, and then we can calculate immediately these epsilons. And one can show that these epsilons should, if the AR1 model is suited, they should appear as memoryless data. Or instead of memory, no memory, you call this white noise. Yeah, maybe I explain here, because we don't make it to chapter 5 with the frequency. I explain here the colors of the noise. Maybe I do this in red. Maybe I do it here. If you draw what is being called a spectrum, then you have on the x-axis frequency. And on the y-axis you have something like intensity or power. And let us now consider the case that we study natural light. And we know, Isaac Newton, light is composed of different components with different frequencies, and but there's no preferred frequency. It is rather flat. Okay, this corresponds to white light, and blue light has shorter frequency. So I will draw blue. Blue light has higher frequencies, my fault. It has such a spectrum. Okay, and now, now, and on the other hand, red light has a dominance of the small frequency, so it would sit here. So excuse me, I used in the beginning the wrong color, so this should be the red color. So make it very thick, okay? More power here to the slow frequencies, okay? And you would call this corresponds to an AR1 process, and also but also other processes. Well, it depends a bit on what the properties of the other processes are, but typically, it corresponds to an AR1 process with A greater than 0. This is exact now. Okay, and if A is equal to 0, then you speak of white noise. Okay, you will see if you, I think it's the sample chapter of the book you have, chapter 5, it has a figure 2. I forgot at the moment, maybe 2.4 or so, which contains the colors. Let me see whether it's here. No, it's on page 174. I don't know whether it's in your book. I mean this figure here. And here you have then the different colors explained. It's figure 5.3 on page 174. Okay, but anyhow, this so this is the story with the colors. Let us proceed now and look on an example, artificial data, artificial AR1 data. We see here scatter plots, two scatter plots, one of the X data, the black points. And we do see some orientation along the one-to-one line, okay? So cold yesterday, cold tomorrow, warm yesterday, warm tomorrow, and so on. This would sit here. On the other hand, these white noise residuals, we just calculated, the blue dots, they do not exhibit a preferred orientation. That means they attest that the AR1 model is a suitable model. Well, this is in fact not a big surprise because I knew what I put in. I put an AR1 in, therefore it should tell me that AR1 is a suitable model. Okay, and the other properties are 200 data points, prescribed A, and hence known A is a 0.717. Okay, I will proceed and give you just some idea about what I found out when I was a postdoc then at the Institute of Mathematics and Statistics in the University of Kent at Canterbury in the UK. I found out that there is a bias in that estimator. If I repeat this simulation game over and over 1,000 times, 1,000,000 times, 1,000,000,000 times, and I look on the average of the estimate, here I get 0.717, then maybe I get 0.694, then 0.701, then 0.688, and so on. I get a billion or so such numbers, and then I draw the average of those, and then I get something that is very close to 0.693. Okay, it is less than 0.7, less than I put in. Okay, and you call this a bias. Okay, this the expectation of what you get is something less than what you put in. 1 minus 2 over n times a. So this is a bias. Okay, I mean 2 over n times a. This is a bias which makes the deviation from 0.7 to 0.693. You will say, well, this bias is not awfully big, 0.7, 0.693. I say you are completely right, but imagine that you don't have 200 points. Yeah? Maybe you have just 20 points or so. Then you are maybe at 0.58 or something like this. And then sometimes it gets severe and severe. Okay? And I also found out that then I studied the literature. First I thought that my computer is doing nonsense, but soon I found out everything is correct. This is an biased estimator. And the thing is that we cannot exactly calculate the bias. We can only approximate this. So this is this symbol means approximately equal to, not exactly equal to. Yeah? So we do an underestimation. This is not nice, of course. Everyone wishes to have a small bias or zero bias, but there are more things behind an estimation. There's also the variance. Okay, and if you take the standard deviation over the 1 billion values, you get approximately this expression here. Okay, which is a value of 0.003. And this helps you then and if you take the square root of that you get, so to say, the standard deviation, the standard error of your estimator. So these are two uncertainty measures for your estimator. And in chapter 3, we will, I think in 10 minutes or so, we will revisit the issue with standard error. And the other things I will now, if you have questions, please let me know, because I will now rather briefly walk through the remainder of the second chapter, and I will omit many things. I beg your pardon in advance. I will proceed now. Excuse me, maybe not, maybe this one I should explain, because this is important for you if you are an experimenter working on data. You can express the situation that a is greater than 0, that you have memory in the data in a certain way, and it is called the effective data size, n prime. So what is this? So usually in the courses I'm not really a football fan, but in the courses I pretend that I'm a football fan, and then I bring the example of well, first we have a situation of complete independent voices, and I ask, what is your favorite team? And then we have maybe Bayern, and maybe then Belgrade. Novi Sad has also a team, likely then Novi Sad. Then we have maybe Leverkusen, Milan, and so on. So maybe we have 20 people and 20 different, or maybe we have 3 from Novi Sad and 2 from Bayern, and then for the rest we have 1. Okay, that we have 20 independent voices. Now, let us assume a hooligan is in our course, and he tells his neighbor, you have to say what I say, otherwise you get problems. Then what happens? First he says, I am a fan of Novi Sad, and then I have to say, oh, I'm also a fan of Novi Sad, and my neighbor says, I like Novi Sad, and so on. So you can imagine by this dependence in between the participants, the number of independent voices is reduced. So let us assume each one has one whole as a neighbor. Then we don't have 20, then we only have 10 independent voices, the independent whole voices, okay? And this is a crucial factor which determines the estimation variance. And let us have a look for the AR1 process and this effective sample size. And you have to bear, or it's a bit complex, because the effective sample size depends also on what estimation problem you study. So here we study a very simple estimation problem, mean estimation. And estimator, mu hat, we take the sample mean, x bar. So this is conventional notation. X bar is a conventional abbreviation for this formula. Take your values, sum them up, divide by their number. Okay, and for that estimation, it was shown that the effective data size follows this expression here. Okay, this is sample size, we know sample size. This is a counter, easy. And here, this is an autocorrelation function. Let me go back a few slides to show you again this function. It is this function here. Okay, so I will plug in this function there, and then we have the effective data size for the AR1 process. And this is then plotted here. Okay, so if that is sample size on the horizontal and the effective sample size on the vertical, then if we would have the no whole situation, then if we have sample size 10, we would also have 10 independent voices. And if we have 100, then we have 100. But if we have a mild form of dependence, then we can be below, okay? And with 0.2, we have this curve here. Then 0.5 we are here, and 0.9 and so on. That means, let us assume with 0.9, maybe you have 100 data points, but you have maybe 1, 2, 3, 4 or 5 independent effective data size, okay? And this is the crucial parameter because it reduces the accuracy of your estimations. Your uncertainties get larger in the presence of persistence. So we can quantify this, and we will use that in the book. And perhaps there's a chance for you to read this in the book. So this was the story with the whole story and the effective sample size. I only mentioned for the paleo people, spacing is not a constant, and therefore it's a bit more tricky. You employ the persistence time, tau, as AR1 parameter. And this formula basically tells you if you are closer to a preceding time point, you remember better. And the distance in time is measured in terms of the persistence time. Excuse me. And the estimation is a bit, let me see. Yeah, it's also stationary. Okay, and this is estimation of the persistence time here. It is a bit more tricky because you can't do an analytic solution. Analytic means you just write the solution and then the equations, and you solve it, and then you have a solution. Yeah, and a formula. But this is not possible here because we can't, no one in the world can solve this formula. The sum, this exponential, not possible. But it's not a problem. You can use numerical mathematics to solve it, to get a value of the minimizer of that. Okay, so by the way, this is called least squares estimation, also a typical approach. This is so to say the data point, and then this is so to say the fitted data point. And then you take the difference, and sorry, it should extend till here. I hope to be able to come back to least squares estimation in the context of linear regression in chapter 4. Let us see. Let me proceed a bit. White noise residuals we have as well. And then we ignore this. And there exist other models. Just be in mind there exist other models, and I will just proceed now. Okay. And you see that the AR1 model is quite a simple model for the memory. Just one parameter, A, or tau if you do paleo and deal with unevenly spaced series. This is very simple, but climate life is complex. Therefore, we have to put the complexity into the other terms. That means we allow also for non-linear trends, not only a linear form, but maybe an acceleration or a change point, maybe even jumps or something like this. And we also admit for outliers, extreme values. Okay? This can be manifestations of very highly non-linear dependence and relations in the climate system you studied. And also this one here, variability, can also be time dependent. So these three terms allow me to put complexity in. Therefore, till now I managed to survive, so to say, in the research literature, and I'm quite okay with how these methods work. So let me now proceed, and I take your questions if there are. Should I repeat something? You need a break? I continue if I take that again. So let me, for the sake of saving some time, ignore the tutorial on the persistence model. I only tell you one or two basic things. The first thing is you can't solve this equation, therefore you use numerical tools, and the software is called tau-est. And it is contained in the software folder, tau-est. And then you can do an exercise on this. And this is an explanation of what the software does. Let me proceed, please. And this is an output of this software. Okay, maybe I lose a word on the bias. We have seen that this estimator is biased. Okay, this one here. If we have an AR1 process with true parameter A, then the expectation of A is unequal to A. This is a bias, systematic error. And we only know approximately this error. And here are some approximations. This formula and that. And I myself also worked on such a formula. But the thing is, we assume that the mean is known. And this is not very realistic, because in reality we don't know the true mean, average temperature at Novi Sad, something like this. We have to measure it and estimate it, okay? And therefore we have to deal with a situation of unknown mean. And then we would subtract from each noise value the sample mean, okay? And therefore this estimator is not the same as for the situation with a known mean. It is different, yeah? And it's more complex. And the only formula I'm aware of is this one by Candle. Okay, this tells you the expectation of your estimator is given by A, and then we have this is a bias, okay? And it's again, it is only an approximation. And for very small values of n, yeah, maybe, yeah, small, and A against 1, the formula may be difficult, and it's not clear whether it holds. And so usually in the courses I tell people, if A is very large, then the bias correction should be used with caution. Okay, let me proceed. And so this gave you a hint on the difficulties in the estimation of the persistence model parameters. Let me see whether there's other things. Well, you can replicate the finding from the book. And well, we are now at the end of the second chapter. And I think it would be a good thing to make maybe a 5-minute break. Is it okay? Yeah? So or maybe, let me take 5 or 6 or 7 minutes. We should begin a bit before 1/2 okay? Then we have, how long do we have? Half an hour? No, 1 hour. This is good. Then we can deal with chapter 3, statistics, and perhaps even with a bit with chapter 4. So see you in 6 or 7 minutes.
Okay, thank you.
I think Biljana has now another.
Yes, I'm here.
Okay.
I'm just sitting at the other.
Yeah.
Here.
I will now proceed. So this is now again a lengthy chapter, and usually in the course I devote 2 hours or so for explaining this. I do not do this here. I put a focus on that stuff here, error bars and confidence intervals. And here I only explain you the principle of obtaining realistic error bars. This is called the Bootstrap. And the remaining things we skip. I beg your pardon, but this saves us some time to make it into chapter 4 for the trend estimation. Okay, we learned that climate comprises trend, outliers or extremes, and noise. We use the sample to make an inference, a guess about the process. That means, in practice, we wish to estimate trend parameters, quantify the probability of extremes, look for cycles and such things. An inferential tool. Now a bit of statistical language. An estimator. Okay, this is a recipe from a book, from a cookbook, a recipe how to calculate what we are after at. Our parameters of interest. It can be just a single parameter, A. It can be also a whole bunch of parameters or even a full function. Okay, we wish to know the true parameters. And if we apply the recipe to the data and get a number, then we are doing an estimation. Okay, this is the second thing. And the numerical value of our estimation, this is called estimate. Okay, and the head reminds us, it denotes that we are doing an estimation and an estimate. Example, we had a few minutes ago, AR1 model, even spacing, just one parameter A has been given, okay, and if we have data which represent the noise component, I mean the residuals, then we can use the data and look in the cookbook, equation 2.4 tells you how to calculate it. Take the product of the neighbors and do this for all, and then do the normalization. This is A heads, okay? An example of an estimation. Okay, now this is important slide because this is, so to say, the essence of the full course. It conveys that we are doing estimations. We are, in a sense, applied statisticians, and we speak the statistical language, the language of uncertainty. So we have the assumption that truth exists, okay? A true parameter, this one here, Greek symbol theta, okay? This can be it can be the A parameter for the AR1, it can be the correlation coefficient or something like this, and so on. We assume that a truth exists For some philosopher of science, this is problematic, but not for us. We assume that truth exists and we wish to estimate, to guess the truth on basis of the sample. Now we learn that we have errors in our measurement devices, the mass spectrometer for 18O. Also, if you do thermometer readings, you're not exactly at the value that exists. You do some measurement errors. If you do paleo, then you take, for example, 18O as an indicator for ice volume. But it is not a perfect ice volume recorder because it sees also other influences, such as from temperature changes. Also, my esteemed colleagues in climate modeling, Cicero and the other centers in the world, they use very sophisticated tools, models. You can say that institutes are built around a model, or a model is a major product of an institute. But still, we learned about the cloud parameterizations and other empirical formula. And then you can't represent every process that runs in reality. You can't represent this in the mathematics of your model. Therefore, also the climate models are not perfect. They also exhibit errors in the data, observation errors. So to make it short, sample size is always finite, and the data have errors. Therefore, you can't assume that your sample delivers the truth. You have an inequality, unequal. Your estimate is not the same as the truth. This is fundamental. Of course, it is not a nice thing, since we humans, we like the truth and we want to know exactly what is happening in real climate, but there's no way, there's no escape. But we can kind of ameliorate the situation in reporting the uncertainty of our guess. How large is typically the deviation? So the estimate deviates from the true value, okay? We are not lost. We can say how large typically is such a deviation. Then we speak about error bars or confidence intervals and other things. So I call this uncertainty measures. They describe how well your guess is, how accurate it is. And this all belongs to the statistical language. We are doing an inference. Okay? That means we wish to know the truth about the climate, and our sample is limited in size and noise influence. We make errors, and this is our duty as a researcher, whether we are early stage researchers or experienced researchers. We have to fight very hard to accurately and reliably determine the uncertainties of our inferences and to report them together with our results. So, for example, if you see, let us assume the average temperature, maybe I call this mu hat. This is temperature at Novi Sad. And then if I read, maybe in April, okay, and then if I read something as, let us say, 12.1 degrees Celsius, the immediate question, I don't say whether it's cold or warm sun, but the question is, what is the uncertainty? How measured? How many data points? What are the assumptions behind? How was the yearly cycle considered? Is there a trend considered in such questions? Otherwise, there's not many things. It could be that maybe the real temperature was maybe 19 and you had a bad instrument, or the real temperature is maybe 12.05 and you had a good instrument. No one knows if you do not try to quantify the uncertainty of your guess. So that means we need statistics. This helps to put our uncertainty into a form to report to others. Okay, now example, we study the PDF, the probability density function of an estimator. So this is our estimator scale, the horizontal scale, okay? And this here is this is a PDF, a function of theta hat. And you see that well, mostly we are sitting somewhere here, but occasionally also there or there. So for the sake of simplicity, I just drew in a Gaussian shape, but you can imagine that also other shapes are possible. Okay, then you can calculate the average. This is this one here. And if we assume that we know that the true value is here, then you can calculate the difference between those. And this is called bias. So this is a way how to express it. Bias for the estimate, bias index theta hat, given by the expectation of your estimator minus the true value. Of course, not always you know the true value, well, hardly ever, but there exist methods to, well, determine and estimate the bias. And so this is one thing of a systematic error. You can compare it if you shoot on a target and you always shoot a bit to the right, then this would be, you have this tendency to the right. Well, in this case, it's to the left because expectation is to the left, so you have a tendency to the left. Okay, and this is one type of uncertainty. The other is the width of the distribution. Okay, if it's very wide, then you shoot this way, and if it's very narrow, then you are shooting this way. Okay, so this is a standard error, that one here. And so these are two ways to quantify the uncertainty, but you can combine both in a handy expression which is called the root mean squared error for theta hat, RMSE for theta hat. So what is this? What is the error? The error is the difference between estimate and real value, okay? Then you square it. This gives you then this. So this was the error. Then the S is the square. This is the square, okay? So it doesn't matter whether one is larger or the other is larger. Then you play the game of the PDF. You take the expectation of this expression. And then you have something which has the same units as theta squared. And physicists prefer to have the similar, well, at least I prefer to have the same units as what is being used. Therefore, I take the square root, R. This stands for root. Okay? One can show that this RMSE comprises standard error and bias in that formula. Okay? So this is a root mean squared error. So you for example, you would say in this example, RMSE is equal to, let's say, 0.07 degree or something like this. This helps tremendously in assessing the accuracy of such a statement. Okay, and how do you come up with this 0.07? Evidently, you have to learn about the devices you are using, about the thermometers, and yeah, you're doing repeated measurements, and you look what are the values. You repeatedly measure with identical measurement conditions. Still, you have some variations in some digit. Okay, you also see here another uncertainty type, which is called confidence interval, or ZI. This stands for confidence interval for the estimate for theta hat. And you have another term in the index, 1 minus 2 times alpha. And 1 minus 2 times alpha, this is called the confidence level. And alpha in the plot would be 5%. Okay, that means the probability that the estimator is below this bound here, theta hat low, is 5%. And for exceeding theta hat u for upper is also 5%. Okay, so in the middle, I use another color. In the middle would be 90%. Okay, so this would be a confidence interval for theta hat at 90%. This would be so and so, so big. So this is an interval which nominally contains the true value with a certain probability 1 minus 2 alpha, the confidence level. Well, I should say perhaps this is called equitailed because 5 is here and 5 is also there. It's not always the situation. This is the wrong way to express it. Mathematicians, sometimes they are strange guys, they also consider unequitailed, maybe here 2% and 8% there. It's possible to do mathematics on that, but in practice it is not of any relevance. So equitailed is perfectly okay. And yeah, now I'm a bit. Let me show this. Now we study a very basic problem: mean estimation of Gaussian white noise. White noise means no memory. We learned this. Okay, and that means all the points are a random draw from a Gaussian with parameter mu, mean, and variance sigma squared, and we use as estimator the sample mean x bar. Okay, and now we may ask, what is the expectation of that estimator under the assumption that the data generating process is Gaussian white noise? Okay, and maybe you have heard this in school. Put the mic here. The expectation of mu, the expectation of x bar is the expectation of that sum and then this is a constant, therefore it is 1 over n times the expectation of the sum, and therefore the expectation of the sum is, you have to believe me, the sum of the expectations 1 over n times the sum is equals from 1 to n over the expectation of x of I. And now, what is the expectation of x of I? It's given here. It is mu. Okay, so we have this is exactly equal to mu. And therefore, this full expectation of the estimator is 1 over n times, and then we have mu, this is for I equal to 1, plus mu, I equal to 2, plus, and so on, plus mu. So this is in fact n times mu. So it's n times mu divided by n, this is mu. Okay, so it's mu and the expectation is given. Okay, that means what we wish to estimate, we get on average. It is a zero bias. Okay, so I just explained this formula here. It is zero bias, it's an unbiased estimator. This can be shown for this simple problem. And well, I think we also do the exercise for the variance, because this is important for the people who work with data and generate data. We also ask, what is the variance of this expression? And let me go back to blue. Now we wish to know the variance of the mean estimator. The variance of x bar is the variance of the sum Now we have to remember, perhaps you had that in school, if you have a constant and calculate the variance, then this goes with 1 over n squared times the variance of the sum times the sum of the variances. And we know that the variance is given by sigma squared. Therefore, it's sigma squared. Okay, it's identical for all the points. Hence, we have 1 over n squared times sigma squared plus sigma squared. This is for the first, for the second point, plus, and so on, plus sigma squared. Therefore, this is n times sigma squared. Hence, it is n times sigma squared divided by n squared. And let me make it green finally. Therefore, this goes away, and we have sigma squared over n. Okay, and if you take the square root of this expression, then we have the standard error. This would be then sigma over square root of n. Okay, so we saw this. The variance is given by sigma squared over n. This expression here, and if we take the square root, then we have sigma times square root of n. So let me make a thought experiment with you to keep you awake. Let us assume you are in a good research group at some university, and you do maybe a postdoc, and you wish to have a paper in Nature, for example, on, well, some climate problems. And very proudly in the weekly group meeting you present new data. And you maybe, you say the first week. You have maybe 100 points, and your uncertainty is maybe you quantify minimum temperature somewhere. Maybe it is, let us assume 1 degree Celsius. Okay, 100 measurements, a week work brings you this uncertainty. You have still material, and you very proudly present it, but then your group supervisor tells you, oh, okay, it's interesting, maybe it's a real thing, but to have a chance to get it even into the review process at Nature. So, by the way, for publishing in Nature, the first hurdle is to make it attractive enough that the associate editor likes it and puts it high on her or his list and sends it out to the reviewers. This is a big challenge, of course. Then so the group supervisor tells you, okay, it's too big. With 1 degree, we hardly ever get into review. So we have to increase, we have to use more samples. I want to have it at 0.5 degrees. Okay? You have to go back to the lab and do more measurements. My question to you now is, how many more measurements do you have to do? So this is the formula. You can write it in the chat, or you can say it by voice. I will wait for a minute or so. Oh, I should say this is a standard error. Okay, this is 1 degree and it should be halved. Okay, so we still have some. Anyone an idea? No, let me wait. Do I see something in the chat?
No, there's nothing in the chat.
Okay. Okay, then I try to give you some ideas. Well, you see that the standard error decreases with sample size at a rate of 1 over square root of number of measurement points. That means you can say the standard error after 1 week, this is therefore sigma over square root of 100 is 1 degree. Okay, now you want to have it halved. Okay, and again I use another color, maybe blue. You want to cut it into a half. Therefore, how many? You should have 400. Okay.
Yes.
Square root of 400. This is the same as before, sigma over square root of 100 times a half, okay? Because square root of 4 is 2. That means you have to have 400 after, well, you need the time. That means you have plus 300 more. Yeah? If you want to halve your error, you have to do 4 times as many points you've got to have. So typically, excuse me, such a formula not only applies to mean estimation, but here it's easy to show. But this is a typical rate at which the error of your estimates decrease with sample size. 1 over the square root of entities you put in. Okay, let me proceed until we get to the Monte Carlo, and then we make another, excuse me. We may also ask, what is the distribution of the estimator, okay? So here we calculated the expectation, and we see that it's 0 bias. Then we calculated the variance, and this is the formula for this. And we calculate now everything. This means what is the distribution, and it can be shown. It is called student's t. A student's t looks similar as a normal. It has a bit heavier tails, but not awfully heavier. And it depends also on the sample sizes. If sample size, well, minus number of estimated parameters. This is called degrees of freedom, or nu. This is a Greek symbol nu. If that is above roughly 30, then the differences between a student's t and a normal, they are negligible. They are almost identical. Okay, so but for small sample sizes you have to be correct. This is therefore the t distribution. And however, the thing is, if we have it, then we can calculate the confidence intervals. Then we know exactly where to place them because you have the full distribution. And we can study this now using a Monte Carlo experiment. And this is therefore, well, now we see the same table as before, but now we take the time to go through it. We take our time that we understand it. In the caption, this is a caption, we see what is being done. The data generating process, usually in the book I first describe what is a data generating process. It is a purely random process. This is the same, it's a white noise process, no memory. So this is a process, Gaussian white noise, Gaussian purely random process. That means the shape also is known, it's a Gaussian. Then we generate a number of random samples, okay, we call this NSIM. I come back to that value in a minute or so. And we prescribe the Gaussian to have a mean exactly as 1 and a standard deviation of 2. This is just, well, these are the values I put in. Okay, and then we calculate the confidence interval, Zi, on basis of this equation. This is a student's T equation with a certain predefined confidence level. So the confidence level is 1 minus 2 alpha. 1 minus 2 times 0.025 is 95%. So we look on 95% confidence intervals. And in dependence on of sample size, we study the coverage. This is the thing I want to draw your attention to. Gamma. This is a coverage of the confidence interval for the sample mean. Okay, what is coverage? You look in how many cases does a confidence interval for a random sample and then the mean calculated on the random sample, in how many cases does it contain this known value of unity? Okay, and this you divide this number of cases by the full number of simulations, by these 4,750,000. And then you see these are the numbers, and they are very close to 95%. So the method works quite well. Okay, now why this number here? Well, it stems from this fact here. No, sorry, my fault. It stems from E. This is a uncertainty for that is given here. Okay, and if you insert this alpha 0.025 and then the number of simulations, then you end up at exactly 0.0001. That means you are accurate up to the 4th digit here. And the simulations, the numbers, they confirm that this is indeed the case. We are not very far away from 0.95, only tiny variations in the last digit, only numerical noise. Well, because our machine can't run infinite amount of simulations, therefore we have to stop, and therefore we have numerical noise. Okay, otherwise we see a perfect agreement between nominal and empirical coverage. That means we completely understand the problem, and our estimator is exact in that sense, and the confidence intervals are exact confidence intervals. And so we learned that if the data generating process is simple, bloody Gaussian white noise, and the estimation problem is simple, bloody mean estimation, then we can write down, we are able to use pen and paper and come with a solution for the CI. We have everything, and our CIs are exact, only numerical noise, as attested by the numerical Monte Carlo simulations. And this also holds if you are interested in standard deviation estimation. It's the same as before. The distribution is called a chi-squared. You can see it in the book. It's no difficulty at all. Also, these CIs are exact. This is in section 3.1.2. And now before we, now let us assume real life, real climate life. We have skewness in the data, right skewness. This, for example, in this plot here, I drew a log normal distribution. Log normal means we take the exponential of a normal. The exponential ensures that everything is positive. It's greater than 0, the domain the values can take. Okay? And so and it has a certain peak here, and it has a long tail there. Okay, this is a log normal distribution, and this log normal is has been frequently used as a model for skewed distributions in nature or in climate environment. Okay, rainfall, perhaps one can think about whether it is well described by a Gaussian distribution, because rainfall can't be below 0, but you can have pretty large values. Of course, there's a matter whether the shape this curve really is log normal or something else. But anyhow, at least the log normal serves well as a model for skewness. But what does happen now to the confidence interval for the sample mean if we still do the Sutton's T? That means if we do so that the data generating process is normal. Now we know, because we put it in, that the distributional assumption is violated. It is not Gaussian, it is log normal. What has happened to the coverage of the confidence interval? And this happens. Instead of 95%, we have 83 or 86 or 92% or so. So we are completely off. That means now the method does not work. And this is a typical situation in climate data analysis, that the assumptions are violated. Okay? And this has, sometimes it has dramatic effects on the accuracy of your results. And therefore, in general, we have to think about methods that apply also for the difficult situation in climate sciences, namely skewed data and persistence. And therefore, let me ignore this. People, me included, turn towards computing-intensive methods who deliver reliable uncertainty measures. And let me show you just the principle of this method called Bootstrap, and then we can have a very last short break before we enter into the next chapter. So the idea is, this is what you have. You have your sample and your estimate. And you use the computer to draw random resamples, only in the computer. And this should preserve the shape, but also the persistence. Okay? And on each resample, you repeat the estimation. On the first one, you get a copy of your estimate, a copy of a head, and the star is used for denoting this copy, and the small counter is denotes this is the first one, this is the second one, and you get 2,000 or so replications. So the replications are copies of the estimator. And these 2,000 values you use then to calculate confidence intervals and uncertainty intervals. So the easiest uncertainty measure also being used in the tutorial is to use the standard deviation over these replications. Okay, and you have to have a certain amount of replications. So usually in the book I recommend 2,000, but for calculation of just the standard deviation, sometimes also 400 is okay. And the book then gives details on how to do this. I only tell you one more thing. The idea of preserving the shape is to randomly draw from the data. You don't impose a certain distributional shape. You take your data and you resample, you put it back, and then you dig into again and again and again. And this gives you a random resample. Some points you sample twice, 3 or 4 times, and some points you miss. But in the next random draw, you draw other values. You draw a random resample of same size n. So this is the same size. And maybe also this stuff for preserving the persistence, you do this not in a point-wise manner, but in a block-wise manner. And the block length should be depending on your persistence time. And then the book gives some formulas, and this is a way how I well designed and wrote the book. First, I give an intro to climate and time series. Then we have to deal with the persistence. And then I have to tell people that still for non-Gaussian shapes and for data with persistence, for time series, we still can apply statistics and obtain realistic and reliable results. This is the idea of the full book. So let me visit shortly the bathroom for 2 or 3 minutes, and then we are back and we quickly go through chapter 4. Not everything, of course, but at least I want to leave you out with an idea what's there, and then you have hopefully time to study yourself. And there's also a time then at the end of the course week, I think it's next week, you can then raise your questions and so let me, excuse me for 2 or 3 minutes, okay?
Okay, see you.
It's okay to proceed?
Yes, we're back.
Okay, good. So we are now in the final chapter. We have 20 or so minutes, and we do the basic stuff. We deal first with fitting a straight line to data. We do a linear regression. And then we do also a nonlinear, which is a bit more advanced, and the third part we ignore. Now we know that we use the series to learn about the climate. And here we are interested in the trend parameters. That means we ignore the outliers, and our focus is on the trend and on the variability. By the way, this is kind of honoring the definition of climate in terms not only of the mean, but also of the variability, S of I. So this is the definition, so meteorologists, Austria, Germany, Russia, and so they worked at the end of the 19th century, and they came up with the suggestion that climate is also, the variability is also a property of climate. And in my view, one should also take into account the extremes. Okay, let us see whether the future adopts this. We can either ignore writing a parametric model, but now we do it and we write a linear model. And this is the linear model. Okay, a linear trend model. This is what is left out of the climate equation, this one here, if we ignore the outliers and if we write a linear trend function. Okay, and it has two parameters. Beta 0 is intercept, beta 1 is slope. And we wish to know the parameters. And we therefore do an estimation, and there exist different ways to estimate this. One is called weighted least squares, WLS. So what is this? We have the data minus fit. Yeah? If you write minus beta 0 plus beta 1 t of I, this is the same as minus beta 0 minus beta 1 t of I, okay? So you have data minus fit, then you square it, then it doesn't matter whether you are above or below the fit line, then you do it as summation over all points, and the fit line that is closer to your data, that means the parameters that bring you your fit line closer to the data, you search for this solution. That means you want to minimize the difference between data points and fit line. Okay, now we come to the issue of weighting, and this is a division by the variability S of I. Why is that being done? Well, there may be time intervals for which your values are more accurate, a smaller climate variability perhaps, or better machines, or a combination of both. And you wish to give those points I a stronger weight. And therefore, if the variability is smaller, and if you divide, this is a division, by something smaller, then the term gets larger. It contributes heavier to the estimation. Okay, so how is the estimation being done? Well, in school, perhaps you have heard, we have a function and we look for an extreme value, namely for the minimum. Therefore, we take the derivative. Delta S S Q W beta 0, beta 1. This is the first derivative with respect to beta 0. And this one we said it should be equal to 0. And then we do the same for beta 1. It also should be 0. Then we have two equations, one here and one there. Two equations for two unknowns. We can solve this. And this is a solution. This is a slope estimate and this is an intercept estimate. Don't get nervous because of these many symbols. It's very elementary mathematics, just a multiplication and addition of points. So the computer does this, as I say, in a nanosecond. It's no problem at all. And we use this abbreviation, this cap W comprises these variabilities. Easy done. Okay, perhaps you have used already linear regression on maybe in Excel or another software. Now you know what the software does if you press the button. It calculates this. It may also employ, if you don't do a weighting, it's also possible. Then you would just ignore this and it also can be solved. Then you call this OLS, ordinary least squares. Let me see, yeah, this is OLS. Okay, so this is also possible. So you see that for an estimation problem, very often there exist different ways to solve it, different estimators. And not all estimators are equally good, and it depends a bit on what the data generating process is. But in this case here, usually OLS is often used in climate sciences. Okay, it's also easy to calculate this. Let me now proceed to a nonlinear model without doing the other stuff. So let us ignore the next slides. Maybe you close your eyes until I tell you. Or maybe, excuse me, open this one. I forgot this figure. This is an example, the climate models. This without humans. This is with humans. That means with greenhouse gases. Okay? That means we have an acceleration of the hydrological cycle. And these lines here, this is a linear OLS slope. And here we see two linear OLS slopes. But we are not so happy about this because, why does it start here and why not there? It's a bit arbitrary. It's not so nice. Okay, now we close our eyes and we proceed to the nonlinear stuff. And I present you here, please open the eyes, a famous curve. Well, it was developed by myself, excuse me. It is called the ramp. It is a model for a climate transition. So this is time and this is trend value. And we have change points. Here's one, here's the other. And it has four parameters: change point times, T2, T1, and change point levels, x2, x1. Okay, this is now a nonlinear function. And it serves to model a transition. So if we do paleo, then time runs this way. And then perhaps, something happened to the system, it changed, and after a while it got a new state, and then it stayed constant, the trend on average. So the task would then be to estimate these parameters. So this is a figure, and this here is the mathematics, the formula. Again, it has these four parameters. We are, of course, interested in fitting a ramp to data. And again, we employ a weighted least squares criterion. Data minus fitted ramp squared, summed, weighted, and this should be a minimum. Okay, now school mathematics does not help us. Well, it helps us for x2 and x1. Then we do the game over the SSQ. After the x1, we can solve this, and also for two equations to unknown. This works, but still we have to find the solutions for T1 and T2. Okay, but unintelligent, well, unelegant as I sometimes behave, I say I'm not so much interested in an elegant solution. I want to have a solution. And I use brute force. I simply try all combinations that are possible. Okay, that is, I say the T1 I search for, that means it is element of the set of time values, T of I, and T2 as well. Okay, and I simply try all the combinations. And I found out that with today's machines, some fast laptops or workstations or even supercomputers, and today's sample sizes, 1,000 or maybe a few thousand or 10,000 data points, it is feasible. We can do it. Therefore, I do it. And this is then the example. This is a northern hemisphere glaciation. I mentioned that in the intro. The time runs from here to there. So between 4 and 2 million years back in time, the northern hemisphere glaciated. The ice was loaded. And the question we asked ourselves in the paper, Maureen, Remo and me, was when did it start? Okay, when did it end? Here. And what is the amplitude? How much delta 18O, delta 18O came? Because this relates then to the change in ice volume. And this in turn further to delta in sea level. Okay? And therefore this is a crucial thing to look what are the causes behind such a fundamental transition in the. So we speak here about the Pliocene. And then after this big change, then we call this the Pleistocene. Okay, in the Pleistocene, this is the age of the ice ages. Yeah, these are big shifts here. Here is warm, less ice, and here is much ice. But in general, we see this tendency towards more ice, the glaciation of the northern hemisphere. Okay, and then we use this Bootstrap resampling approach to generate error bars. And let me just quickly go through this. We need the Bootstrap resampling, and we resample from the residuals, data minus ramp fit. Okay, these are the unweighted residuals. You divide by variability or estimated variability, you get the weighted residuals, and these are the values you put into the moving block Bootstrap. Okay, these resampling blockwise from the original residuals. And these you add back to the fit curve, you get a resample on which you reapply the estimation. Then you get 400 or so copies. 400 times you get, for example, change point time 1 and also change point time 2. And you can calculate then the standard error over the 400 copies. And this gives you then these numbers. Okay, I think this is now an exercise. This is what can be done with nonlinear regression. So it's a kind of an advanced estimation technique. So the problem is now complex. And also the distributional and memory assumptions are typically climate, namely non-Gaussian distributions and persistence, and still we can work on such data. This one we ignore. This would lead us too far. And with great pleasure, I would hear your questions on that before well, first the questions. Are there any?
I have a question, Manfred.
Yeah.
Yesterday, because we have here students who deal with different scientific problems, and some of them are in paleoclimate, as you heard yesterday, as you heard in the morning. And this ramp function that you showed us, nonlinear regression, can it be used to find the changes in trend in the data?
Yes, of course, of course.
When the trend started, for example, if we have upward trend and downward trend, we can pinpoint the exact time where it started with some kind of confidence interval.
Yeah, well, but the big assumption is, let me show you again, or maybe I directly proceed to the tutorial. The big assumption is that the ramp model is suitable. That means it is a constant here and it is constant there. And not always. This is a situation in climatology. Okay, but it depends a bit on the data you have. If you see that there's a systematic decrease, then perhaps the ramp is not so well suited. So in practice, I often help me, then I narrow down the fit interval. Then I say, let us assume we have such a data. Then I would say, let's look only in that interval and fit a ramp to the data within that interval. So it's a bit a tricky thing. On the other hand, it brings you dangerously close to a situation where you try to tweak the fit interval such that you observe what you wish to observe. This is dangerous, of course, but you have to behave responsible, of course. But there exists another option, maybe for that person you mentioned, not the ramp, but the break model. So let me just show this and inform. We don't do the tutorial. We don't have the time for this. But there is a software for the ramp. It is called RampFits. It's in the folder. And there is, you find on my website, Manfred, I think it's without, Mudelsee.com. It's a paper from 2000 in computers and geosciences. You can download it from my website, and this is the original paper for the ramp. And this also, I think, has a tutorial. And you can also download the software from my website. Let me now turn your attention finally to the other model, to the what I call the break. This is an example from the Arctic River. And now we fit a break model to these data here. You see the ramp would not be a good model because, well, we don't know exactly whether this is... we should allow that this changes, then a further change. Okay, so this is a break, it's down, up, but it could also as well be slightly up and strongly up. For example, if you think about global warming, an acceleration of warming happened at this point. Okay, it also has 4 parameters, and this is the formula. And you fit the model using weighted least squares as before. Now it's easier. You just search for one change point. It's easy to fit. Done in a, well, easy. And then the software is also there. It's called BreakFit. Of course, I use original software from RamFit and I adapted it to fit the break model. And perhaps this is with a combination of the ramp and the break, I think people are then in a not so bad situation to quantify changes and change points and accelerations and pauses and such phenomena.
Thank you. Does anybody else have any questions? No.
Then let me finish this day. It was, well, it was an experience for all of us, I would say, by giving you some reading material. Let me see, where is it? We ignore this stuff here, the non-parametric. And okay, I think I put another paper here, but this is you find it on my website, but also in the reading material. This is a review paper I wrote where more or less I put the things together in a paper instead of a lecture. And in this paper here, we look on the Cenozoic, on the past 65 million years, on major climate transitions, and quantify each transition with uncertainty interval. Evidently, maybe not this evening, but maybe tomorrow evening. So my aim really is to write accessibly for the students, for you, and I would be pleased to receive your feedback. It was a great pleasure and a big experience for me doing this online tutorial and online lecturing. It's the first time for me, and I think it's an interesting format, at least as long as COVID enforces us to do it this way.